So we now want to give a global and rather detailed overview of what inheritance, generalization and specialization are in the context of the object-oriented programming model, and in particular C++ in the moment. So this is fairly analytical approach to discovering class hierarchies, and if class hierarchies are good in some sense. So let's begin. We want to model hierarchies of classes, object-oriented inheritance hierarchies, let's say. And you'll need it in computational finance because many applications work with a hierarchy of classes. So you've got a base class, a number of derived classes we've spoken about a little bit, and in particular we want to have good hierarchy so that we can get flexible C++ code. And in C++ we talk about a base class and its derived classes, and the derived classes specialize the functionality in the base class. So this is the basic scenario we want to talk about, and at the moment we have to find the hierarchies of classes if they're in the first place applicable, because when you develop software, hierarchies is like an optimization technique. Your main objective in the course is to get option pricing formula correct, up and running first of all, and later on you can actually make it more flexible and abstract. Nonetheless, we have to discuss what inheritance is, because in the future slides we'll be talking about the implementation of base and derived classes, specialization in C++. So we start off with a general class, which will be the base class, and we specialize classes from it. And of course you can get the number of levels is infinite in principle, so you can derive classes from the classes which are derived from more classes, etc., etc. Whether it's a good idea to make very deep hierarchies is debatable, and if it's correct or not is another discussion. But basically, when you use inheritance, you get new functionality in specialized classes or modified functionality, and we'll see exactly how this works later on. So we'll and the potential dangers as well. So here's a little bit of cognitive psychology, which is the basis of object orientation, you might say. One of the things about people is that when you divide the world into entities or concepts, you wish to achieve a certain level of cognitive economy. So that's a big you don't want to be thinking about all the for example, all the points like 1, 1, 2. You just want to say, oh, I've got an abstraction called point, and it's got objects, of course. So in order to be able to learn, remember and perceive the concepts in our world, we categorize things, we group things, we classify things around us. So you can group things at a very high level. You can say everything is an animal, for example. And you've got reptiles and dangerous animals and mammals and birds and so on. But there are different levels, so you have to seek a balance between the level of economy. So a word called animal and informativeness. So these are negatively correlated. So the more abstract your terms are, the less information. And the more information, the less abstract it is. So basically, let me draw a diagram here, just to motivate it conceptually, because we're in the conceptual level now mode. If I've got it at a very high level here, as I go down the hierarchies, whatever that might be, I get more and more information. I get to the level of objects eventually. So the very high level is very abstract, and it's sort of in between abstract, and at the very bottom we've got lots of information, but it's very concrete. So you might have here an animal, etc. And at the very bottom, let's say let me see if I can write it properly. Everybody knows what a pigeon is, right? So this is a very simple example, but it's meant to show what the concept forming process is. So at a very high level, we've got animals, now we've got pigeons. So there's a lot of hierarchies in between, lots of concepts in between. Okay, and this will be exactly the same when you're developing class hierarchies for finance, except you're not working with animals and pigeons, you're working with options and bonds and concepts from options. Okay, so categorization. So how do we categorize all my objects? And there are a number of different views you can take. This is part of psychology as well. Frege, who was a German logician, actually in fact laid the foundations for object-oriented programming, and we'll see in a moment why. In particular, he talked about object concepts. These were atomic units, so these are something you can think about. They've got a certain coherence together, and they're like little atoms which we combine into bigger molecules. And we got 4 defining views for actually for modeling objects, and each one can be mapped into C++ using advanced C++ techniques. And the 4 views are, let me go back to my pen here. 4 views are the defining attribute. This is Frege's approach. This is typical object oriented. We've got prototype view, we've got exemplar view, and explanation based view. So this is all fairly advanced, and I don't know if you need it in the beginning for the course. On the other hand, when you get to more advanced applications and maybe in later life, you'll realize that if you're using only the defining attribute approach, in other words everything's fixed, you're going to get into trouble, your software anyway. So the first view is called defining attribute. Attribute is like state or member data, you might say. So Frege has the following: a concept, which is really a class in the moment, has a set of defining attributes or semantic features. So what's the essential properties of a certain concept, and that's it. So once you've done the defining attributes, you're in business, you can actually create your classes. Frege calls it not classes and objects. He calls it intension and extension. So intention is really the class, so it defines what the essential properties are to be a member of the concept. So this is class in C++. So animal is an intention, so it's like a class. An extension, these are all the objects which are members of the concept. So birds, pigeons, and so on are all members. So that's just a fancy way of saying in real life the intension is the class name, and the extension are the objects in your class. Consequences. So of this approach, the meaning of a concept is captured by the conjunction "and" of its attributes. So if you've got a number of attributes, the class is the defining attributes. So it's like a bird flies and has wings, for example. Of course, what about birds which cannot fly, like penguins? But at the moment we're assuming this kind of so you can't have a concept saying, oh, it has wings and does not fly. It would not constitute a bird in Frege's definition. The attributes are atomic units, so these are primitives and are building blocks of concepts. So a concept is built up from its attributes. Each attribute is necessary, and all of them are jointly sufficient to define an instance of the concept. So if you've found all your attributes in your concept, you need them for each instance. You cannot have an instance of a concept saying I've got a bird which can fly but has no wings or something. So this is the first one. What is and what is not a member of the so this should be more consequences. This should be 4, 5 and 6. So what is and what is not a member of the category is clearly defined. In other words, If it's got no wings, it can't be a bird. And if it's got wings and it can fly, it's a bird. So it's very clear cut between members and non-members. So it's very obvious. All members of the concept are equally representative. So if you've got a pigeon, it's just as representative of the class as an eagle, for example, which also has wings and can fly. The Frege's approach allows us to define concept hierarchies. These are class hierarchies. So as you go down the specialization chain, as it were, you get more and more specific attributes. So here we got the different levels. So going from high level to low level. So here's the highest level, here's the middle level, let's say, and here's the lowest level. So when you go from here down below, so in the upper parts you got less attributes, like animal, for example. So here's attribute animal, here's attribute mammal, and this could be tiger. So animals have very few attributes, mammals get a bit more, and tigers have even more. So the superordinate level is the very top level, we'll talk about in a moment, is here. So the superordinate level would be the class animals in this case. Okay, so that's just to review the Frege approach. Basically what you do is you discover the attributes, your semantic units, building blocks of your concept, and you build your concept from these attributes. And these attributes are necessary and sufficient to specify what an object is of the concept. That's the first approach. What are the disadvantages of the defining attribute view? In real life, the category members are not all equally representative. So you may have another animal which is like a marsupial or something, which is a mammal and a reptile or something. In real life, the concept boundaries tend to change, so things change, the attributes become less and more. So the theory doesn't predict certain level structure, three-level structures in the moment we'll talk about, and some attributes tend to be more important than others in reality. Concept instability, that's the big one. So when you create a class in real practical terms, it changes because somebody else has a different view of the concept. Let's go back to even the simple example here of animals. What are the attributes of a tiger you want to model? Depends who you are. Different people have different views of a tiger and what they want to do with tigers, or what to model in tigers, and of course how to find the defining attributes of a class is not so easy. So the prototype view, there's a prototype structure. So you don't have a classes, and you've got some prototype object which is the best example of the concept. So for example, a pigeon is that the best example of a bird, for example. So yeah, a pigeon can fly, it's got wings and so on, it's got a beak, it eats worms and so on. So we've got to make a long story short, a collection of characteristic attributes. So there's no set of necessary and sufficient attributes in order to say that, for example, a pigeon is part of a bird family. So they're necessary but not sufficient. So it's a bit fuzzy. Some instances may slip into different categories. So disadvantages, it's incomplete as an account of the sort of knowledge people have about concepts. So it's not complete. The attributes, just looking at attributes, are not sufficient because people compare the relationships between attributes more than they actually talk about attributes. So it's not a good approach. The exemplar based view, instead of working top down from concept to instance, which we did already, we take very specific instances to discover concepts. We don't look at all instances. So instead of saying birds on wings, which I talked about just a moment ago, we look at a crow and a sparrow. So it's a bit like a prototype, but even more specific. So we look at crows and sparrows, and when we get a new instance, we can say, does it look like a crow and a sparrow? Okay. The disadvantages of exemplar: it's very difficult to handle abstract knowledge. If your whole world is talking about crows and sparrows, it's very difficult to say in a moment all birds are creatures. So the whole point about it is it depends on similarity. So the similarity between crows and sparrows, for example. Okay, the last view, which has consequences later on for C++, and in particular when you're designing classes which can be extended, is that we have another view which is not attribute based anymore, because in the previous three views you looked at the attributes, the similarity between the attributes, between a crow and a sparrow. Both can fly and have beaks. Prototype is the same, and the defining attribute is the same. But we want similarities between classes which have not got to do with attributes, but which have got to do with the causal information, background information. So it could be functionality, based on functionality. So a very good example of the explanation-based view is dangerous and non-dangerous animals. What constitutes a dangerous animal is not, or a dangerous bird, is not necessarily the beak, for example, which can eat you up, or the claws or something. It could be something else. So we want to have a hierarchy of animals: dangerous hierarchy, non-dangerous hierarchy. So it's a bit different. So the explanation view is a bit more dynamic. The concepts are determined by actions. A dangerous bird can eat you up, basically, a dangerous animal, and a non-dangerous animal possibly not. So the concepts, they've got attributes, but it's the relationship between the attributes. So for example, if I've got flight, the attributes, because a number of birds have light bones, they can actually fly. So the attribute of flight, or the semantic action, has got to do with light bones. So birds with light bones can fly more easily. So the coherence of your concept is from the underlying knowledge of the concepts, what they actually do, not from the similarity. Okay. So that was a very short overview of the different kinds of ways of finding concept hierarchies and classes and the attributes. It's probably a bit too advanced for the or non-relevant at the moment, but it's good to know that that there are different ways to find classes and their member data, which is the attributes, and class hierarchies. We now talk about a very important hierarchy. It's like a template. It's a classification which is pretty universal. So we now want to group our classes into hierarchies. So like a chicken is an animal, is it? Yeah, but it's it's a bird as well. So we want to create a class hierarchy. We call them conceptual hierarchies, and we want to every concept which we have put into the hierarchy at some level. And behind the scenes, your brain is trying to order all this knowledge into groups and so on. And it turns out that there are basically three levels of concepts, which will have their implementation in C++ later on. So the three levels are first, second, and third, going from the highest order to the lowest order. The first order is the so-called superordinate level. So it's the general, it's the highest level, it's the general designation for very general concepts. So at the very highest level, for example, you've got furniture. Yeah, everybody knows what furniture is. At the very lowest level, at the lowest level, subordinate level, specific types of objects. These are really my favorite armchair is sitting in my room, or the chair I'm sitting on now. So it's a real object with a. It's not a class; it's a real object. So it's I've got one favorite armchair, which I never sit in, but it's a real object. And in between, we've got the basic level. This corresponds to specific concepts, specific classes, like a chair. It could be any chair. It could be a chair you're sitting on. And these are the, let's say, the templates which we will use to map to C++ class hierarchies when we go to the computational part of the course. So at least you'll know why you're doing something, instead of maybe just automatically creating class hierarchies without knowing what the underlying ideas are. Okay, the superordinate level tends to have very few attributes. So if we go back to furniture here, what's the attribute of furniture? I'm not sure, no idea. Whereas the lowest level, my favorite armchair, I know everything about, but also a chair. How many legs has it, and what's the size, and so on. You can start thinking in more concrete terms. At the subordinate level, which is at the very lowest level, there are too many attributes. If I'm thinking about my favorite armchair, I'm thinking about the where it's positioned in the house and the color and so on. There's just too much information without being able to make more abstractions. Most adults tend to start at the basic level, so a chair. So people can think about chairs and start thinking about what chairs are in general. That's the way young children learn. So the category members have the same overall shape, so at the basic level. So you form a mental picture basically at the intermediate level. So these are the three levels in general, and you'll see in a moment when you're actually programming. You'll have a base class here, it's called the superordinate level. You'll have a real class here, which is derived from the base level, and at the very lowest level you'll have objects with real attributes and values and so on. Concept instability, and this is the same as class instability in C++. The representation changes according to the context in which it appears. So if you've got a class, depending on what the functionality is, which is needed, everything will change. And that's the well-known phenomenon in object-oriented hierarchies. Everything changes. So when something changes in the base class, all the derived classes have to change as well. So this can be disastrous. So basically the problem is caused by behavior, new behavior. So we have basically context-sensitive information. So this can be a problem. Now, back to real life, you might say. We've done the theory of classes, concept hierarchies. What's the relationship or the issues with C++? Developers use these views when creating classes, either implicitly or explicitly, but you need to know which choice are you making and what the consequences are. So I'm using defining attribute hierarchies, prototypes, exemplars, or the explanation view. And many legacy systems with deep hierarchies are having these problems as well. It's a blind spot. So we have to use an appropriate design pattern, but that's for later on. Okay, so let's take some examples, and later on when we get to the computational finance part of the course, you'll see some more real life things. So here, for example, I got payoff hierarchy. So at the very top level you got an abstract payoff class, which is a superordinate. At the middle level you have call payoffs, possibly pot payoffs, and at the lowest level you'll have real life objects. Instrument hierarchies is a good one. So the superordinate level is instrument. At the basic level you might have an option, and at lower levels you might have call options, for example. A very good application of object orientation is the two-dimensional shape hierarchies, lines and circles and polylines and more complex shapes, which we actually started off doing in my company for CAD/CAM. So we wrote one of the first C++ libraries for CAD/CAM using all these object-oriented systems. This was a long time ago. We got finite difference methods we'll be talking about. So you got a hierarchy of finite difference methods. So the base class will be finite difference method, and derived classes will be well-known finite difference methods such as Crank-Nicholson, Euler method, and so on. We've also got hierarchies of PDEs. So you have PDE, partial differential equations. So you might have the base class to be just PDE with nothing in it, and the basic level would be two-factor PDEs, one-factor PDEs, and at the lowest level you might have Black-Scholes PDE. Just let me draw the diagram just to make it slightly more concrete. So at the top level we'll have a PDE, any PDE. We might have at the next level a so-called, let me write it down, partly a parabolic PDE. So it's a time-dependent problem. And at the lowest level, which is what we're interested in, we might have Black-Scholes PDE. Okay? Or other PDEs like constant elasticity or volatility PDE. So here we got the superordinate level with nice, very few attributes with behavior. Here we've got a parabolic equation, more detail, and at the lowest level you got lots of detail, but Black-Scholes equation needs data as well. So these are the three hierarchies. And in the moment, in this particular section, we'll be showing you how to implement all of this in C++. At least you know where it's coming from. We've also got data interpolation hierarchies, different kinds of interpolators, bond instruments, and so on. So it's all quite practical. At least you know what you're doing and why you're doing it. Okay, we finished with inheritance and hierarchies. Something else which is very important, which is used less by developers quite a lot. It's not used so much by developers because people have been a little bit brainwashed by inheritance. I've now got a class C2 which uses the C1 in some way. So I'm building a class C2 with C1 as one of its components. So on the client software calls a method or a member function in C2, C2 delegates or forwards the message to C1. So in fact, as I've said, inheritance is an optimization technique. We can emulate inheritance with aggregation. Just by, instead of saying C2 is derived from C1, I just embed C1 and C2, and all the new functions in C2 will just delegate to C1. It's a form of reusability at object level. Now here are some examples of aggregation. Think of a two-dimensional point we've programmed already. A polyline consists of a number of points. A bond class has cash flows and schedules. So there's a whole cash flow and schedule dates. So it's got a whole bunch of dates and a whole bunch of cash flows according to each date. So it's an aggregation. If I'm solving finite difference methods, I need to solve finite difference methods always pertains to a PDE. So the finite difference object has a pointer, as it were, to a PDE object. In other words, the PDE object is embedded in the finite difference method. STL, which we'll talk about later on. Stack class. A stack class is a data container, and on a stack you can pop some information from the stack, and you can push some information onto your stack. It's got an embedded store, so internally the data store which implements my STL stack can be a vector, is just like an array with indexing, a list or a queue. So a queue is first in, first out. So these are examples of aggregation. Now we're finished. So this was a high-level discussion of some classes. It's something you need to think about as you go on in life the next 2 days, 2 years, 20 years, because it's you're actually modeling your classes in computational finance. So how are you going to do it? So the techniques I talked about are kind of out of scope in some sense, because they're a part of a broader analysis and design of larger systems. Nonetheless, it's important. We talked about the dangers of classical attribute-based theory. That's basically the problem. And a lot of these topics have similarities, analogies with the design patterns. If you know about the book by Gang of 4 design patterns, which we will not discuss really here, but we will see some examples of actually how to implement all of the stuff we've done here and what the advantages are. Okay, so just a bit of a quiz, just to get you up to speed before you come to the computational finance part of the course, and also programming in C++ in a moment. How would you've got a one-factor option pricing formula and options. So how would you create a hierarchy of options? So everybody knows put options, call options, chooser options, shout options, American options, early exercise, Bermudan options. How would you do it in each view? So that's a very deep question. Would you model the hierarchy according to the attributes? So for example, put and call have a strike price, of course. A chooser option is neither a put nor a call. You can choose. Create a hierarchy for the two-dimensional classes. Shapes, points, lines, polygons, squares, ellipses. How do you do it? Is an ellipse a special kind of circle, or is a circle a special kind of ellipse? I don't know. Or is it neither? Would you use aggregation instead of inheritance? Some people say that inheritance is an optimization technique. In that sense, in the sense it's not absolutely necessary. What do you mean? Here's a hierarchy. I've got an array class. So an array class can create a contiguous number of elements in memory, but it's got no mathematical operations. So you just create it. You can access the members of your array. You can actually change the values. I now want to create a vector class, which is it is an array, of course. You can index the elements of your vector as in the array, but I want extra functions. So for example, I want to be able to add two vector objects together. I want to be able to multiply a vector by a factor. I want to subtract two vectors, inner products, whatever. So it's a mathematical array class. How would I do it? First option is a. In other words, do I see vector as a specialization of an array, or can I create my vector class with an embedded array class, and all the new functionality in vector or existing functionality in array is delegated to array? So in other words, I'm using the aggregation here. So these are fairly extensive and tricky questions. It's like the meaning of life in object-oriented programming land, because every wrong decision will have major consequences. Concerning the hierarchy of classes, we've made all of this in production software in the 1990s. So there's a follow-on remark is, if you have lots of domain knowledge, you will be able to create your classes better. So if you really understand what finance is and all of these different kinds of options, you'll have a better class hierarchy and better classes and more flexible classes. So that's a very important issue here. Okay, so we've survived some cognitive psychology, something to think about, and it'll become much more obvious when we go to part number 6, which is computational finance, because we'll be doing all sorts of hierarchies to make our software beautiful and flexible and all of that sort of nice stuff. So we'll take a break here, and I will see you later. Bye.